Hey everybody, welcome to lecture 5.2 on the dot product. And in this video, we're going to talk about the other notion of information contained in a vector, which is the direction of the vector. We discussed a little bit about directions of vectors at the end of 5.1, where we talked about parallel vectors having angles 0 or pi, and perpendicular or orthogonal vectors having angle pi over 2, or having a right angle between them. In this video, we're going to fully describe all possible angles between vectors algebraically, meaning using their coordinate representations, which are easier to deal with, especially as we move to higher dimensional vectors. So the key notion tying all of this together is the dot product. The dot product also turns out to help us compute lengths of vectors or magnitudes, but we already have a formula for that, so we won't talk about it as much. And the goals in this video are to define and calculate the dot product of two vectors, and then to use the dot product to understand the geometric relationship between two vectors. Finally, we're going to also study the notion of vector and scalar projections of one vector onto another, and this also uses the dot product. So these are different ways of understanding the geometry of vectors using something called the dot product, which I'm going to introduce now. So if we start with vectors u and v in the xy plane, meaning they have two displacement coordinates, v1, v2, and u1, u2, then the dot product of these two vectors is a number or a scalar, and that scalar is defined as follows. If I take the vector v and dot product with u, then the output is the number v1 times u1 plus v2 times u2. The way to think about this, or the way to do this formula fast without having to repeat, v1, u2, v1, u1, v2, u2 every time, is to think about taking the vector u, taking its coordinates and sticking them right on top of the coordinates of v, or superimposing them, and then multiplying and adding up the result. So the way that we say this is we multiply coordinate-wise and we add along coordinates. And for three-dimensional vectors, that same procedure works exactly the same way. If I have v dot u and v has these coordinates and u has these coordinates, then we're going to multiply the first coordinates together, the second coordinates together, and the third coordinates together and add up each of those three results. This pattern can be extended to define the dot product of two vectors in any dimension. And notice that the vectors have to be in the same dimension in order for the coordinates to line up and make the dot product make sense. So that's what the dot product is by definition, but it's more important to know what it actually means. Before we see what the geometric interpretation of the dot product is, let's just practice computing with this formula. So if you want to try this on your own, this is something you can do without my help. I'm going to switch over to the tablet and do this with you, but you're welcome to pause the video now and try this for yourself. And notice in both examples, I'm actually using three-dimensional vectors right away. We don't need to start with two-dimensional vectors to understand this. This works in any dimension, and it's not that hard to do. So with coordinate notation, if I have 2, 3, -1, and 4, 1, 5, and I want to take their dot product, remember I should get out a number, not a new vector. And the way I'm going to do this is I'm going to take the first matching coordinates, 2 times 4, multiply them together. Then I'm going to switch to the second coordinate where I have 3 times 1 and match those up. And finally, in the last coordinate, I have a -1 and a 5. Notice again, I'm multiplying each coordinate and then I'm adding up the result. And I'll just write it out in a couple steps. I'll get an 8, a 3, and a -5. And let's see, if I do my addition carefully, I should get a dot product of 6. So we don't know what this means yet, but these two vectors have a dot product of 6. So it's some way of measuring the relationship between these two vectors. If instead we have two vectors that are written in I, J, K notation, remember I, J, and K are our standard basis vectors pointing along the x-axis, y-axis, and z-axis by 1 unit each. It's easier to translate things into coordinates, in my opinion. So I'm going to write each of these two vectors in terms of their coordinates. -2i means they're -2 displacement in the x direction. There's no j's, so there's 0 for the y coordinate, and there are 4 k's, so there's 4 units of displacement in the z direction. And likewise, the coordinates for the second vector are 1, 2, -1. Now things are in coordinate notation. It's a little cleaner to look at. And we can take their dot product by multiplying coordinate-wise. -2 times 1, 0 times 2, and 4 times -1, and then adding up the result. So just to be really, really thorough about this, that's -2 plus 0 minus 4. We get a result of -6. So in the first example, the relationship between these two vectors as measured by the dot product was the number 6. And in the second example, which were two completely different vectors, the relationship was measured by the number -6. So it's possible to get out negative numbers. It will also be possible to get out 0. And the interpretation will be the important part here. So just for now, we're computing numbers. Let's get to that interpretation next to make this worth our while. Before we do that, to make computation easier, it's nice to have the following facts at our disposal. The dot product of two vectors satisfies the following three properties. Dot product is commutative, meaning it doesn't matter which way I choose to multiply them, multiply the two vectors, and you can check this coordinate-wise. Doesn't matter which way I multiply two real numbers in each coordinate. The dot product is also distributive, which sometimes makes computations easier. If I can express one of my vectors as a sum of two simpler vectors, v and w, then I can compute the dot product of u with each of those vectors and then add up the resulting numbers. And finally, if I have scalars m and n multiplied by each of the things I'm trying to take the dot product of, I can factor out all of those numbers out to the front and just compute the dot product of the original vectors u and v by themselves. Okay, so let's start getting into the geometric interpretation of the dot product. First, and I'll state this using two theorems. First of all, for parallel vectors, which we know have an angle of 0 or pi, or 0 degrees or 180 degrees between them, they point in the same or opposite directions. In other words, the dot product actually tells you which direction they point in relation to each other. So the dot product will always be either the length of u times the length of v, or negative the length of u times the length of v. And if it's the positive or negative product of those lengths, those two cases tell you exactly which directions the vectors are pointing with respect to each other. So this theorem tells you everything in that case about the geometric relation between the two vectors. So the dot product is positive and equal to length of u times length of v if u and v point in the same direction. And the dot product is negative and equal to negative length of u times length of v if u and v are pointing in the opposite directions from each other. I left a little space on the slide if you're sketching notes on the slide for you to draw a picture here. I'm not going to do this, but we can certainly do this in class. So that's the first theorem that makes sense of parallel vectors and the dot product between them. And there's only two options. Either it's the positive product of their lengths or it's the negative product of their lengths. The next case that we saw in the last video of angles was the notion of orthogonal or perpendicular vectors. And the dot product interprets this as well. If we have two vectors, u and v, that are at a right angle to each other, also called orthogonal, then their dot product is 0. It turns out that, and we'll see this by the end of this video, that if the dot product is 0, then the vectors have to be orthogonal. So this is, it turns out, a complete characterization of orthogonal or perpendicular vectors. The vectors are perpendicular exactly when their dot product is 0. And in some sense, the dot product is originally construed to be a detecting tool for when two vectors are orthogonal, when they form a 90-degree angle between them. So this one's not so easy to see, but if you pick some examples of orthogonal vectors that you know, such as the vectors I and j from the last video in our ij standard basis notation, you'll see that their dot product is 0. And if you choose different pairs of orthogonal vectors, just writing down some 90-degree, a right triangle, and pick the coordinates of the vertices, write down the displacement vectors for the two legs of that right triangle, and then compute the dot product of those two vectors, you'll always get 0. And this theorem tells you that this is always the case with orthogonal vectors. So here's the real beauty of the dot product. Two vectors don't have to form angles of 0, pi, or pi/2 radians between them. So they don't have to be parallel or orthogonal. But luckily, we can always use a little bit of geometric trickery, namely writing v as a sum of two special vectors called vproj and vorth, and express v as this sum and then compute dot products with u using the distributive property of the dot product from a few slides ago. So I'm going to explain this geometrically on this slide. We'll also see this done in terms of coordinates later. But if I have a vector u and a vector v, and I want to compute the dot product of u times v, and I don't know that they are parallel or orthogonal, I can always draw a triangle where one of the legs is parallel to u, or in the same direction as u, more specifically, and the other leg is orthogonal or perpendicular to u, and those two legs of the triangle add up to give the hypotenuse being v. So there are the names for these two legs, by the way, are the projection of v onto u and the orthogonal projection of v off of u, or with respect to u. These are technical names for these two vectors, but geometrically it's pretty easy just to draw a triangle like this and draw these two vectors this way. Now the hard part becomes when we want to compute the actual coordinates of these vectors as displacement vectors, but we'll see ways of doing that in the future. For now, if we use the distributive property of the dot product, we can write v as vproj plus vorth. And because u and vorth are orthogonal to each other, here they form a 90-degree angle in the picture, their dot product is 0 by the previous theorem. On the other hand, u and vproj are parallel to each other, and in this case, they point in the same direction. If v were making an obtuse angle with u, then it would be pointing in a different direction. But u and vproj, when we take their dot product by the first theorem, has the dot product is equal to plus or minus the product of their two lengths. So in general, this is how we compute the dot product between two vectors u and v, no matter what the direction is between them. U times v is equal to plus or minus the product of u times the product of the length of u and the length of vproj. Now, how do we possibly compute vproj and vorth? That's a more delicate matter, but for now, I want to point out the following value, which is called the scalar projection of v onto u. So if I take the vector v and I project it onto u to get this vector vproj pointing in the same direction, I want to know at least what the length of this is, because then I can scale u down to get this vector vproj. And the length of this will be exactly the dot product of u and v divided by the length of u. Now, this is not a very useful formula if you don't know what the dot product u times v is, but theoretically, this is a good tool to be able to compute vproj with. If we can somehow figure out the dot product, we can also compute vproj, or conversely, if we know what the projected vector is and we know what this triangle looks like, we can extract the dot product from it using this formula. So here's the grand master theorem that governs all angles between vectors and thereby describes directions of vectors in at least so far in 2 dimensions. So I'll state it as a theorem. If u and v are two vectors with the same initial point so that they meet at some angle theta, then the following formula holds. And in fact, the theorem says this holds in any dimension. So let's forget about 2-dimensional space. The dot product u times v is always equal to the length of u times the length of v times cosine of theta. This is where trigonometry and angles come in. The dot product can be computed by a product of two lengths of the vectors times cosine of the angle that they form. You should think of this as the master formula for comparing any two vectors in any dimensions. They have to be in the same dimension, of course, to make sense of this. Keep in mind that cosine of theta, if you think about the unit circle, it's always positive when theta is in the first quadrant, or theta is between 0 and pi/2. It's always negative when theta is in the second quadrant, or theta is between pi/2 and pi. At that 90-degree angle, or theta equals pi/2 radians, cosine of theta is exactly 0. And that's going to correspond to when the vectors are orthogonal, by the way. So you can see that this formula captures all of the notions of parallel and orthogonal that we've already discussed, but it also tells us if the angle between two vectors is acute, obtuse, or parallel or right. So again, this theorem knows everything there is to know about the angle or the relative direction between two vectors. Let's practice with this formula by computing an angle between two vectors in 3 dimensions. So you have the formula on the previous slide if you want to give this a shot. And I copied the formula down here if you want to take a look at it again. If you want to give this a shot without my help, then pause the video now and try to compute the angle theta in this formula. All right, so I've rearranged the formula to almost solve for theta. We'll need to take an arc cosine or an inverse cosine at the end, but I'll just leave it as cosine of theta equals this stuff for now. So the key ingredients I need are the following expressions. The dot product of u and v, and then the lengths of each of the two vectors. And when we're computing the lengths, I'll mention how the dot product also relates to the length, since we haven't quite discussed that yet. Although it certainly comes up in this formula, there's a more direct relation. So let's start with u dot v, and let's just line up their coordinates side by side so we can compute this easily. I don't want to add them, I want to take their dot product, 1, 1, 0. Let's make a little more space. And again, we're just going to superimpose the coordinates, multiply coordinate-wise, and add up. Well, 2 of the things are 0, so I actually just get 1 in this case. So the dot product between these two vectors is 1. If these were, so first of all, these are not orthogonal vectors. We just learned that because if they were orthogonal, they'd have to have a dot product of 0. So we know they have to have some angle that's not a right angle between them. Let's continue by computing their the lengths of each vector and plugging them into the formula to find theta, what that angle is. They could still be parallel, but actually we also know they're not parallel since one is not a scalar multiple of the other. So we already know just by looking at them that they're not parallel. So there's some interesting angle between the two vectors. The comment I wanted to make about the length formula is that the length formula, and this works for any vector in any dimension, can also be computed by taking the dot product of u with itself and taking the square root. So I want you to think about why that's true. But assuming that that's true, I'm just going to compute using our original length formula, where I take the square of the first component, the square of the second component, this is for u, by the way, the square of the third component, add those up and take the square root. Here I'm going to get a 2 under the radical, so the length of this vector is square root of 2. And actually, we should get the same number for v since it has the same number of 1s and 0s, but I'll just do this carefully. So just to remind you, to keep you thinking about this, this is the same as taking the dot product of v with itself and taking the square root. And think about that at some point if you haven't already paused to think about it. Here's what this looks like with the coordinates plugged in for v. And again, we're going to get the square root of 2. So let's, I'm going to move this formula down here now to compute cosine of theta from these values. We saw that the dot product was 1. And the lengths of each of the vectors was square root of 2. So if I multiply that out, I'll get 1/2 for the cosine value. So cosine of theta equals 1/2. Can you now think of a theta angle on the unit circle that has cosine of 1/2? Well, if you think about it for a little bit, you'll end up getting pi over 3 as the angle in the first quadrant. And for cosine, the possible, at least, if we want to solve this uniquely for theta, we'd apply arc cosine, and the arc cosine has outputs between 0 and pi radians, which is exactly what we wanted. We don't want to talk about negative or overextended angles that are in the third and fourth quadrants. So in this case, the angle between these two vectors, both of length square root of 2, is equal to pi over 3 radians. So they form an acute angle. And the reason that we knew it was acute, if you look back at the theorem, was we got a positive dot product between them. So there we go. There's an angle computation using the cosine formula. Like I said a couple times, this theorem, this angle, this cosine formula knows everything there is to know about angles and geometry between two different vectors. And there are a couple problems we can immediately apply this to, such as the notion of work, which is a notion in physics relating force and displacement. So if we have a force acting on an object, we say that the force works on the object if it moves the object in the direction of the force. And work is actually a specific measurement we can make of this situation, which if we have a force acting by some displacement s, some number of meters or inches or feet that the force moves that object by, then the work performed by that force on that object is F times S. Work equals force times displacement. We can visualize all of these things using vectors where the displacement vector shows how much the block or the object was displaced by the force. If the force is moving in the same direction as the block, then the force vector and the displacement vector will be in the same direction. But more generally, force and displacement may not be in the same direction. For example, there will be a homework problem where some amount of force is required to keep a block from sliding down a plank, which has some angle it makes with the ground. And in order to apply that force and keep the block from being displaced, or in other words, to cancel out the potential displacement of the force of gravity, we won't have a force acting in the same direction as the force of gravity in that example. The way to basically compute things in general is using dot products rather than just multiplying lengths of vectors. We can instead multiply the vectors directly using the dot products. So the way this works in higher dimensions, or not necessarily in higher dimensions, but if the force and displacement vectors are not pointing in the same direction, then the work is a number still, and it's computed as the dot product of the force vector and the displacement vector, which if you look back at our discussion of the definition of the dot product for vectors of different directions, then it's the same as the projected vector f proj onto the displacement vector dotted with the displacement vector. So in any case, the work equals force times displacement formula with vectors in higher dimensions always looks like W equals F dotted with S. Here's some summary questions for you to think about. What algebraic properties does a dot product share with real number multiplication? And can you think of ways that these are different or behave differently? Next, and probably the most important question coming from this video is, what is the significance of the dot product of two vectors? And in particular, what's the interpretation of the dot product of two parallel vectors? How is the angle between two vectors related to their dot product? And finally, what is that scalar projection number and how do you compute it? What does it mean and how do you compute it? Those are both important questions. That's it for this video. I'll see you next time for more three-dimensional and higher vector manipulations.